Yes, I'm James Carl. I took this class probably in 2011. So it's been a while, but yeah, I'm going to be taking over for Matt. I've been working at Ford for the last 10 years. So.
Yeah, and I'm like running through the basement right now. We get in at 6 o'clock and do calisthenics and stuff.
Okay, so you'll see both of them during lab sections this week, and then there will be a GSI and IA as well.
Yeah, they're nice. I too. You probably got some pictures of them.
Yeah.
All right.
All right. All right, actually, so I have a bet. I'm going to take a picture of you all. Sorry, didn't really ask for consent. But the whole point here is I'm supposed to learn your names by the end of the semester. And there's a bet that I can't do it. Hold on, you got to pick a seat because I'm going to remember spatially where everybody is. No, it's fine.
I'm going to shuffle around every class.
What's your name?
Gabriel.
Nailed it. Gabriel's the one that moves every time. Already put it in there. All right, here we go. Thank you. Okay. No, you can do anything you want. But people typically stay in the same areas, right? And then so the trick is if you're going to learn people's name, you memory map it by location. So you need some context. We'll see. There's 72 of you and 2 on the wait list. My ability to know names, I don't even know his name now, is gone. So, or is not very good. So we'll see if it happens. Okay. So you're here for embedded systems. Great. A little bit about me. So I went to University of Washington. I was a really electrical engineer. Don't tell my computer science colleagues that I'm really electrical engineer. I'm hiding in here with them. But I didn't actually go here. I went here for a little while for my graduate school, but I really went here. So I spent 5 years working full-time at Intel Research Seattle and just happened to take classes every once in a while. In fact, the department wanted to kick me out at one point because they're like, well, you don't even have an advisor. I'm like, yeah, but I'm working full-time over here doing research. Anyways, did that. Did a postdoc in computer science, working on heart implants, so wirelessly powered heart implants that had this cool embedded system in it. After that, became a research scientist at Intel in Oregon. Went back there. Then my career took a little bit of a turn. I ended up working at Disney Research in Pittsburgh, started off there, and then worked my way up. Ended up being a lab director at Disney Research in LA. And then, well, the pendulum of what industry considers research and what I wanted to do swung. They want to do more development work. So then that's why I came here. So I've been here about 6 years now. All right. Yeah.
Can I ask what you did at Disney?
Sure. So Disney, the goal of the Disney Research Lab at that point was to do research for the entire Walt Disney Company. And so they have like movies, movie studios, animation studios. They own Pixar. So there's lots of graphics work. They also own ABC. So there's like automated broadcast work. They had parks and resorts. That's where I primarily was. They're the largest company with public-facing robots of any type. So there was lots of robotics work. That's why they're at CMU. And then they also had like cruise ships and all these other things. So our job was to kind of do research for the entire company and anything they did. And I did wireless systems and sensors. And then all of a sudden, you know what they had? At Intel, I worked on wireless power. It's very boring. All of a sudden, in Disney, they had these things called humans. All these guests walking around. So then I took a shift in my career and started working on sensors to measure and understand human behavior. That's more or less what I do now. Any other questions? Yeah. I did research that wasn't necessarily focused on a product, so it was kind of more open-ended research. Some of my projects turned into products. So at Intel, I made basically wirelessly powered RFID tag that had a full microcontroller and all these extra cool things that ended up turning into a product that was sold in Brazil to be the first over-the-air encrypted RFID car tracking product or tolling system product. So sometimes my research goes into product, but not all the time. Any other questions? Okay. So, yeah. So please take the survey. You've already done that. Homework 1 has been assigned. It's due next week. Pre-labs are going to start this week, or labs are going to start this week. Normally, you have to do your pre-labs before you get to pre-lab. or before you get to lab, that's what pre-labs are. This week, you can just do them in lab because we're just starting out. Usually have a week to do the labs. Exam times are set. You can go look on the website. So block those off, yeah?
So are we gonna have lab this week then?
Yes, absolutely. So exam times are set. We're just waiting on, we have times, we're just waiting on locations of them. And then you should be enrolled in Piazza and Gradescope. So anybody who's not in one of those, please come see me after class. We'll make sure you get you enrolled. All right, so today we're gonna talk about what is embedded systems. Overview of the course, and then we're going to talk about the STM32 architecture, which is the microcontroller that we're going to be using. This is to set you guys up for Lab 1 this week. And we're going to do a little bit of primer on GPIO, which means general purpose input outputs. All right, so embedded systems. I would say embedded systems are everywhere, right? So embedded systems in a lot of ways are the computers that don't have screens, right? Don't have keyboards, don't have human-facing interfaces. So you see them all over transportation. I think the stat was like there's 100 different little computers, microcontrollers in modern cars. You also see them in medical equipment. These things do, of course, have screens oftentimes, but they're more purpose built for a particular task. Home and office, even a microwave at this point can be considered an embedded system. And then, we have smart TVs. They're, at this point, some of them are actually running OSs, but typically you might consider that to be an embedded system. So, take an example of, look at one of them. So here's a Nest thermostat. So what do we have here? We have an LCD display, a rotary encoder. So this is a way to input data. Here's inside of it. You got a ARM Cortex-8, so it's an application class processor. They also have an STM or a ARM Cortex M3, which is very similar to the microcontroller you'll be learning about in this class. Wi-Fi, Zigbee, NAND flash, external flash, two motion, IR motion sensors, USB management and power management, a rechargeable battery, and can you believe it? They also packed in here the ability to measure temperature. Amazing. Also humidity. So my question to you, why in the world does Google and Nest need an application grade processor in a thermostat?
To collect data on you.
Ooh, well, let's say that, okay, that's fair. We can talk about the ethics of this, but what would they say they're trying to accomplish?
So I can have my temperature on my phone, or I could go, out of my house and say, oh, my house is really hot before I get home. Let's change
Okay,
that.
so why they trying to connect? Any other reasons?
Smart home ecosystem.
Yeah, so when they made this thing, why do you need to have Wi-Fi and Bluetooth and Zigbee just to connect to the internet? Well, they're trying to position this in the marketplace as a hub, right? So that all your wireless objects can connect to this thing. That's how Nest originally pitched this product. Really, all you need is a single thermistor. That's about it. If you really want to get fancy, maybe STM32 in a display so you can set the schedule. But just saying that these are components of a modern embedded systems. Okay. So let's take a quick detour and figure out what are the forces that are causing us to get to the point where we can afford that, right? This thing has more computational power than it took us to take humans to the moon. It's the first time, right? Far more capabilities, and what's the reason why we can get this so cheaply in our houses today? All right, so we can look at the number of computers per person, all right, as a function of time. So let's see. So this is a function of time. So we're in 2024, so a little bit past here, and here's log scale of the number of computers. And we start seeing that originally you start off with a mainframe, so you got one per enterprise, right? So all of University of Michigan might have one computer. Then you get down to a mini computer, so that might be one, in this case, for a department. You get down to a workstation, one computer per family for home, one computer per person, and now we're in the realm of multiple computers per person, computing devices. Look forward, you think about that. So this is just looking at technology trends. Over time, more computers per person. We think about the volume, right? So we have size versus time over here. We had mainframes that were very large. All those things started shrinking down, smaller and smaller and smaller. Okay. And then we can think about price as well. The cost of a mainframe in adjusted US dollars is far, far more expensive than a smartphone or whatever we have today. Okay. So how is this happening? So there's an axiom called Bell's Law here, which is every decade a new class of competing devices come out. Now it's a little hard, you can't predict it. If you could predict it, you're gonna make millions, but you can't predict it. In fact, right now we're gonna discuss what is the class of computers that exists right now in the 2020s. Okay? But it basically says roughly every decade, lower price computers based, class forms based on new programming paradigms, networking, interfaces results in a new class of computing established in the industry. All right. We can look at some other forces because of that. Well, not all of us, but you've probably heard about Moore's Law, right? And this is really an economic argument that the number of transistors is going to double every 18 to 24 months. And then, yes, there was Dennard scaling, which made this possible in the beginning, but right now it's really about, hey, the market's going to bear this idea that people will pay for doubling processor count every 18 to 24 months because they can, through processes, can make these things smaller and more efficient. So it's really a statement about economics, not like some fundamental law that has to happen. We can look at trends in wireless communication. So here we see wired, so Ethernet, light, or optical fiber, all those, you can see speeds increasing in time. We have wired and wireless in this context is base stations like GSM cellular services, things that a company would put large infrastructure in. And then the nomadics are like Wi-Fi, Bluetooth, those sort of things. And it's kind of interesting to see in the future, those two lines are going to cross each other. So what does it mean when I can have, I'm faster for wireless than I am for wired? What new things will we design based on that paradigm that we wouldn't design now? You look at trends in batteries. So this is cost, time, and then density. So we can see that approximately every 9 to 14 years, there's a doubling rate at which the energy density of batteries will increase. So meaning that you move forward in time, you get more and more dense batteries. Now, this is not an economics law like Dennard scaling or Moore's Law. This is more like a material scientist have a breakthrough like every few years, and that allows this trend to go forward. But you can imagine that the amount of time you can keep an amount of computation alive and going between recharges is only going to increase with time. Right? Batteries are going to allow that. You can do more with the devices that you have now. So what's driving this? So we talked a little bit about Moore's Law. Dennard scaling was this idea that you could, in a semiconductor lithography, that you could shrink all the features and power would shrink and size would shrink as well. It doesn't really happen anymore, but it was a driving force for a long time. The result of Moore's Law and Dennard scaling is that if we hold the number of transistors constant, if we don't increase how many gates Intel puts into their stuff, if you just keep that constant and then you use more and more advanced processor nodes, then the amount of power and costs that you have starts dropping exponentially. So now, all of a sudden, because of these two forces, we keep small computer resources. That's why we can have really small microcontrollers now that are really cheap. You can get something, that's approximately the computational power of an Apple IIe for $3 now, right? And it's only because they made the processes so efficient for other purposes. We have other technologies like LCDs and plasma and other display technology. We have lots of new MEMS sensors that allow us to sense the world around us, new memory technologies. Threshold scaling has allowed us to have really, really low power devices, or at least have things in certain states that are low power. And there's also new wireless protocols and architectures coming out, and energy harvesting, okay? So my question to you is, what's next? It's kind of what you're here to learn, right? You're here to get the basic tools to build things, embedded systems things. So you should start thinking about what is that next class of devices that's going to exist in the marketplace. So why don't you take, here we see that from mainframes all the way down to smartphones. So why don't you guys take 90 seconds, talk to each other, and come up with a theory of what you think, when we look back in 10 years, what we think this new class of computing devices that you probably have right now are.
Yeah.
Someone's in the back. Our slice.
Here's you got in your head.
I don't think anyone really has it.
Sure, put it right there. Like that.
I think it's
You look like a weirdo.
We're thinking either VR.
True? So can we make a broader statement than just one product? Yeah. Maybe we can call that a larger class of wearables.
You can transport it to a person.
What do you think? What's the next class of computing device?
How much the devices cost, everything provided under.
It's kind of in that wearable space.
It's easier to take.
What do you guys think? What's the next class of computing devices? You probably actually have one at home.
Yeah. How many of these devices are there?
Okay. What about things that aren't wearable though?
Because I think
Anybody got an IoT device at home? Alexa?
anything you can think of.
Okay.
signed up for, but I might
Thought of like.
double major.
Wait, what's your double major?
I can't say.
Vector AP.
Moving your hands. Yeah, I'm too.
All right, so what do we think?
I know, keep saying, please. Yeah.
What do we think is here? What's the next class of computing device?
Job search.
You go to a grocery store, you buy eggs and milk, and you would have processors and wireless devices in them, in which they would just say, hey, I'm expired now.
Ooh. How's that different from RFID? I think we have that. We could put a RFID tag in there. It has a piece of silicon. It gets wirelessly powered. It has sensors. Sometimes they have sensors in there. Okay. What else? What are some other ideas?
VR and AR.
Okay. Yep, we have lots of those. Is there a more general way of thinking about AR, VR? Or what else kind of falls in that category?
Wearable tech.
Wearable tech?
We were having this discussion on like
Real loud, because I'm old.
would you consider cloud computers to be like a new class of computers?
Ooh, that's fine. So we got wearables. So we'll come back to that idea in a second. So we got earbuds, we got glasses, we got Fitbits. Some people got heart rate monitors. Okay, so there's one class, and then we have cloud computers in general. Okay.
I'm thinking like the Neuralink brain chip.
Yeah. Well, I guess we'd also want to think about what's there today. So you probably have one of these things. Most likely. We don't all have, at least in this plot, right? So I agree that Neuralink is probably a feature for something.
Say Alexa.
Okay, so IoT stuff at home. So, okay. Anything else? Yeah.
Maybe like AI that goes along with like the tech ecosystems we have now. So that if you have a file on your computer and you're just on your phone, you could potentially access it through like a voice command or something like that.
All right, so a big idea here is that we have the cloud behind us, right? So if we're gonna have, so we could make an argument that, we don't need physical anything anymore. The size here is 0 because it's all AI and in the cloud, okay? That's one vision of the future. We'll find out if that's true. But if there was a physical device, we'd probably say that here's a widget, some gadget, and then it's connected to the cloud to give you those extra computational resources. Any other ideas? Yeah?
Okay, so I remember I read this one sci-fi comic, and like in that there's this the setting is similar to real world, but like probably like 20, 30 years in the future, and like they have this thing where like a hive where every device has some amount of processing power, and they kind of like share it with each other.
Okay, so kind of Skynet. We're going for Skynet.
It is kind of like Skynet because in that story, a sentient AI gets released.
All right. I think we're well past 2020. No matter how good OpenAI is. Any other ideas about what this next class of computers that we're probably in right now are? Okay. So one possible answer is my own thinking here. So we got mobile sensing computing devices without traditional interfaces, connected to the internet and backed by cloud computing, right? So if I think about Alexa or Google Home or something, here is a device that is purpose-built. It's not general purpose computing. It's supposed to be ambient in my environment, just usable. And some of that compute is offloaded, right? And it can do that because we have fast internet now, right? So if you think about all those trends we talked about, those are coming together to make new classes of devices. Okay. So for me, I think the future or the class of computing devices we're looking at now is IoT something. So I think that's embedded systems. And clearly it's going to be backed by cloud computing and all that other stuff. If this is something you're interested in philosophizing about, what is that next branch of technology? What is the future going to hold? There's people that work on this. My research lab does this, but there's a great article by Gregory Abowd on the future of ubiquitous computing. So a lot of the things that we're talking about now started as from Xerox PARC back in the 70s, and this idea of ubiquitous computing, basically computing that's embedded in the world around us, that would be connected to something like the cloud. They didn't have that term back then. So if you're interested, you can read more about this, and then I teach a class in winter that kind of delves into these ideas. Okay. Well, let's go back to answer a question about what is embedded systems, because we didn't really get there. So here we'll go through a few examples. So we have a gaming PC versus a gaming console. Okay. So one costs over $2,000, one is $400 or so, so one's cheaper. The gaming PC the hardware is configurable, or at least hard to configure, but it is configurable. The other one is easy to set up, easy to use, but it only does really one thing. One's larger, heavier, consumes more power. One has been optimized for a specific task. Your gaming PC can do everything, right? It can do gaming, but you can do music playback, scientific computing, can do your taxes, does whatever you want to do. I agree that more modern gaming PCs can do those. Sometimes they give you that option, but really they are fixed function devices. So I'd argue that embedded systems is about making trade-offs, about where you're going to say, well, I can't do everything, but I'm going to use all this cool technology as comes out to drive towards one specific goal and deliver a product or a capability to consumers. So I'll ask you guys, is a mobile phone an embedded system? You take 30 seconds, talk amongst yourselves.
This program go.
See if I can get rid of
I mean, you can put it on a PlayStation, you can put it on a phone.
If you want, it's just gonna submit the project.
What do you think? Is it an embedded system?
Yes.
Embedded system? Okay, anybody say no?
I think after smartphone, iPhone kind of period, it just became a computer because it runs an operating system.
Okay.
As all the older phones were very specific. They were all kind of different OSs.
And I would even say if we go over here to the the Motorola D-Track, this is almost analog, right? They didn't even really even need a processor in it, right? Any other ideas?
How many features until it stops being embedded?
Ooh, this is a good question.
Because I know you can play Snake on a Nokia.
Okay. All right, so I think we're getting to the same idea, right? So maybe there was a transition here. Maybe over here, analog, embedded system, and then somewhere over here, maybe it's not an embedded system anymore, okay? And we're kind of debating what makes a quality of an embedded system versus a general computer.
I guess as an idea, maybe if we remove the label mobile phone and we make it a lifestyle companion, as if that's like what the device is, maybe these smartphones are more so, they fit that specific purpose rather than a normal computer, right? Because you can't really get as much compute on a phone than you could like a regular desktop.
I believe it's true that you can't get as much compute, but I could still have a very limited laptop. It still could be a computer. What do you think?
Maybe
Gabriel, right? Got you. All right. Oh, you got me.
maybe the ability to add additional features that weren't originally conceived with the device into the computer.
All right, I like that.
I think it's probably like not really a line, like it's probably like a platypus or like, I don't know. This can't be a good example, but it's like something that's kind of like a mix of both, like mammal and a bird or something, like or like embedded in general purpose, just kind of like a.
So there's a vague line is what I think you're getting to. It's hard to define the line. Okay, I'm gonna ask you guys, what year do you think it changed? If we had to go in here, you had to put a year. When do you think it happened? You can take 30 seconds to talk to yourselves or talk with your neighbors.
7. That's somewhere there.
Did you just ask OpenAI? You just ask ChatGPT?
Video came out.
Okay. All right, what do you think? When did this happen? What was the defining factors? Take a guess, yeah.
2007.
Oh, man. See, okay, so I didn't say this, but you can go download these slides beforehand, but I keep them redacted so that you guys actually say engaged. So you can go online and get the slides. But this guy over here got me. Exactly the reason. I would say 2008, right? And this is really when the App Store launched, right? So now you had an ability to put other software on there. Before it was a closed ecosystem, right? So we could put, we can make a little Nintendo, right? That's not, that's still like a Game Boy, I mean. That's still an embedded system. It just says one thing, right? And it's what it's designed, what the designer designed for it. But all of a sudden now, they started allowing anybody to write software for it. And I think that, in my mind at least, that's when it transitioned to a general purpose computer. So you guys can debate with me and say it's something else, that's fine. That's what I would put as a definition. All right. How about an autonomous vehicle? Is that an embedded system? I can take some time to brainstorm.
That scares me. I mean, even now, it's happening.
All right, what do we think? Is the autonomous car an embedded system?
Yes, except some cars like have like the tablet feature, and the tablet's not embedded, but everything else is.
Okay, anybody? It's not wrong. What else you got?
I would say it's a collection of embedded systems because you've got the area for LiDAR, you've got the navigation console, you've got steering control, etc.
Again, I must have put the wrong slides up because yes, they got LiDAR. This is exactly a slide I have. You got LiDAR, you got cameras, you got rear sensor modules all over the place. So I would say this is a collection of embedded systems. Okay, maybe we would call it a robot instead, right? So this is just happening a robot without, that's not a humanoid robot. All right, let's try another one. Let's see how we do. How about an SD card? Is an SD card an embedded system?
Yeah. I don't know.
It's a trick question.
Yeah. It's not like certified.
I mean, like it does something. Like it has memory.
Yeah.
It's like this is like an Arduino.
I guess that's a good way to do it.
Yeah.
I don't think it is.
All right, what do you think?
Because it does bidirectional communication, there has to be some sort of like microprocessor in there negotiating that, thus making it an embedded system.
That's good reasoning. I guess the counter argument was it's just memory. Memory in itself is not a embedded system. Anybody else have any other ideas? All right. So I'm going to say that, yes, it's an embedded system, but it's not obvious. And it was never supposed to be obvious to you. This is how most embedded systems are. When you go push on the brake, you're not like, aha, I'm using an embedded system, right? You're just happy your ABS didn't, kept you from slipping down the ice. So in most flash drives now, they actually have ARM7 or ARM3 or maybe an 8051. So a microcontroller in there is handling data transfer back and forth. It's true for communication purposes, but also if you think about the memory itself, it's not perfect, right? And we think about this as a noisy channel in the sense that it will put bits down, but it may, due to manufacturing issues or cosmic rays or whatever it is, there may be errors in it. So actually what you're doing is you're doing error correction. They're doing forward error correction. So they're putting more bits down than you need to store the information, and then it's decoding those bits on the microcontroller and then sending them off to your computer so that it can be more error-free. And this allowed the manufacturers of the disk drives to not have to make perfect ones, especially as you get much larger gigabyte size. It's hard to keep every single transistor or transistor pair perfect. So they overcome the problems by adding embedded system, adding a processor in there to do a task. Is that convincing?
Good question. Like, they put down the on the label it says the size. Does they put on the number of bits that a perfect one would have, or like number of bits the average one would have?
I think they're saying to you as a consumer, this is what we're going to guarantee. This is the size that we're going to give you. This is accessible. You find that oftentimes the industry does something called binning. So they do this with processors as well. They say, I have a processor that's not quite good. Maybe the process SKU makes it get really hot. So I'm just going to sell it at a lower value, lower tier, and just say it's like, I don't know what Intel's doing, an i3 now, right, instead of an i7. It's still the same piece of silicon. It's just that, manufacturing process didn't get quite where I wanted it. Instead of throwing it away, I'm just going to resell it as a different tier. So my guess, that same sort of logic goes with memory, where you're just saying like, a whole bunch of gates are destroyed and I can't get to the second gig, so I'm just going to sell this as 1 gig. And so who knows what you actually get underneath the hood. You just get what the package says. That's what's accessible to you. All right. So last exercise here. Can you guys come up with a definition of what embedded systems are? We kept on kind of circling around it. Might be helpful to think about things that definitely are embedded systems, things that are not, and then things that are the borderline. So come up with take 60 seconds, come up with a definition, and we'll talk about it.
Something that gets
I don't want to say that.
yeah.
Or has.
That can be added to
So you say that's not
This is like
All right, what do you think? Can we come up with a few definitions for embedded systems?
Multi-specific.
Is that what Wikipedia says? That's what I read on my iPad. Okay. Sorry, say it again then.
What's the opposite of a general purpose computer?
Okay.
Those specific purpose computer.
Okay. All right. Sounds good. How about somebody else?
Anything with a chip or a processor in it that you wouldn't necessarily consider a computer.
Ooh, I don't know, that's kind of good. How about somebody else? A brave person. I beat up on that guy a little bit too much. Somebody who's brave.
Specific purpose computer that like can't be easily accessed by the user.
Okay.
Also often doesn't have like a system to update it or change whatever's inside.
Or at least it's not user updatable, right? The company may want you to update the firmware, but it's not like, okay. All right, so here are some textbooks from, or some definitions from textbooks, and they all have their limitations. So a digital system that provides a service as part of a larger system, maybe, but an Alexa, I'd say, is like a, well, I guess it's not completely self-contained considering it needs Wi-Fi, but most thermostats or microwave is self-contained, so, but that's okay. A device that includes a programmable computer but is not itself a general purpose computer. Okay. A less visible computer. I like this one. I like this one. This is the least descriptive, but maybe the most accurate, or covers the most cases. Single function, tightly constrained reactive computing system. Okay. And reactive here, the idea is not that it's self-contained in the sense that you have a machine that can compute pi all by itself. It's a machine that senses the world around it, takes inputs, does something, and stimulates the world in some way, right? Sends some data out. So it's not just a self-contained device. And then lastly, from Wikipedia, it was not the Wikipedia quote, but a computing system that with dedicated function within a larger mechanical or electrical system, often with real-time computing constraints. And I think, me specifically, I recognize the real-time part of that. Typically, we're talking about things that are not high latency, maybe not real-time in the most structured definition of real-time is, but it means it's doing computation and coming back with a solution quickly. Any other definitions that I may have missed? Or anything you think here is just wrong?
Maybe like the single function part. I feel like there's a lot of embedded systems that like, you know, you can like have input and output. So technically that's two separate.
Oh wait, where's the single function?
Like the fourth one.
Oh, single function, I think what they mean is purpose built for one task. And that task maybe have input and output, but it's not like it's gonna be a thermostat and do your taxes, right?
I have a question about the definition of like programmable. Is it like it should be user programmable? Or is it programmable by the manufacturer and it technically could be programmed, but it's not meant to be programmed by you?
We don't know. Who knows? I mean, I think that's a fine delineation between the two. I would say most embedded systems that I've worked with, I can't go, unless I'm the developer, I can't change them as a user. But I don't know what they meant here. Any other thoughts? Yeah.
Is it like
a computer cannot be an embedded system? Like you can't just say that it's like a subgroup of embedded systems where it's general purpose?
I guess we could make whatever, the chart however we want, but I would say that a general purpose computer has a lineage and is significantly different than an embedded system. At least I could identify that.
Well, because like originally, because like with the scale with the phone that you showed,
yeah.
Like the computer goes to the exact same scale. Like originally the computer was designed for one task.
No, if we go all the way back, I mean, those were the best general purpose computers we had at the time, right? You could put a program in, you put punch cards into them, they would do calculations for you.
Calculations, like that was its purpose.
I think we would go beyond. I think they were. Well, I guess it's depending if they were Turing complete or not, right? Like, but I think we would consider those to be general purpose computers. While we would not consider embedded systems to be, which are more fixed functioned. I don't know. These are debatable things. Any other thoughts? All right. I'll give you one example from my own research back almost 15 years now about when embedded systems get weird. So some of you may be familiar with far field RFID. So these are RFID tags. They're about this big, little, like stickers. These have little microcontroller, they have ASICs in them. So a piece of silicon in there that's trying to harvest RF energy to boot up, looks at the protocol coming in, and if it's being talked to, it'll send back data, reflect data back, telling its ID. So it's not a general purpose computer, but it's just an ASIC. And then you have an RFID reader, which is sending RF power and data to those devices. So these are battery free. And the range here is like 10 meters or so. Okay. So one of the projects I did is I wanted to make, how do we make the most functional RFID tag? So we put a full MSP430 on this thing. So it had a range of like 4 to 9 meters. So MSP430 is a 16-bit microcontroller, and it has all the things that you would think about embedded systems. So it has some harvesting, some rectifying, so we could get the RF energy in, had power management, had a demodulator for communication. So there's the microcontroller. So 16 bits, like 32K of flash, not too big. 3D accelerometers, temperature sensors, voltage rectifier measurements, so some analog measurements, LEDs, and external EEPROM as well, and a watch crystal to keep track of time, but no batteries, okay? So what would happen, it would basically harvest energy from the RFID reader. Whenever it was ready, it would boot up, try and do some computational tasks, and send data back. So here's an example. I don't know if the sound will come through. I don't know if this will play. So here, one of my colleagues had made a theremin out of this. Basically, it's measuring the acceleration of gravity down. So there's the RFID reader, send RF energy, boots up, measures the acceleration of gravity down, calculates a packet, sends it back, and then that encodes the orientation of Saturn there. So as he moves his hand, you can see Saturn move. So now we have these wirelessly powered computing devices that you can embed in things. And in fact, a professor here, I wasn't working with him at the time, but he went and embedded a bunch of it in his foundation when he redid his house. So he could go and measure if the foundation was moving or not. And we ended up open sourcing this project, and there's like 50 universities around the world that use these things in their own research. Okay. Any questions? Okay. So key takeaways. So technology, I want you to think about just in general, the technology and market forces that are driving the evolution of computing. Part of your job, in this semester is to learn the principles of embedded systems, but pretty soon you're going to be out there in the world, right, as an engineer, and you are going to make the decision, hey, I know technology is going in this direction, right? And all I need to do is make sure that I'm ready for it. When, say, wireless speeds equal wired speeds for communication, what product should my company be developing then? If you know what the trends are, you know what you have a good idea of what projects or products to make a bet on. By specializing in embedded systems, enable new computing devices that were not previously possible. So this is the act of specializing and making those trade-offs gives you something that a general purpose computer typically can't do. And generally, there's no precise definition of what embedded systems are. but you should be able to identify one when you see one. You should be able to look at it. ScanDisk one's a little difficult because you can't open it up. You have never done that, but generally, given enough time and information, you should be able to identify if it's a general purpose computer or embedded system. All right, so we're gonna go on, talk a little about the course a little bit, and then go over microcontrollers. Anybody have any questions so far? Okay. So you already met Matt. You met James. They're the primary lab instructors for this class. Tom Kurlikowski is a graduate student, UMC alum. He'll be teaching a couple of the lab sections along with IA Alec that will also be there. So look for these people in lab. There should be 2 of them in each lab section, and they'll be rotating around. And there's also open hours that you can find on the lab calendar. So the goals of the course, learn and implement embedded systems, hardware and software interfaces, learn to design embedded systems, thinking about both the software, the firmware that you need, and the hardware. This can be a challenging class in the sense you have to kind of be good at both. You don't have to be excellent, but you have to understand what your software is doing, you have to understand how that's impacting the hardware. And it can be the hardware constraints of your processor, but also the external world when you get to your projects. You'll have the opportunity to design and develop non-trivial projects. And this will be the foundation of embedded systems learning for the rest of your life. I often think of this class as that where we teach you the basics so you can read the data sheet on your own. If anybody's looked at a data sheet, you're like, I don't understand any of this. I don't even understand how it's structured. After taking this class, you at least can go to almost any ARM manual and pick it up and be like, all right, I have the background to read the manual to get the rest of the information that I need. So the best compliment I ever got, I was helping some guy in lab. I asked him if he needed help, and he said, no, you've taught me enough. I know how to read the manual. I was like, all right, I'm done. Like, as a professor, you now can teach yourself. The contrary is when I never took an embedded systems class until much later, and I was working those MSP 430s, and I just spent about a year banging my head, didn't understand the fundamentals, and just kind of like brute forced my way into understanding embedded systems. So hopefully you guys will have a better time than I did. As most of you know, we have prereqs for the class. So intro to logic. 370 is pretty foundational, although we take it probably the next step of that for that size class architecture. So we'll be doing the Cortex M3 and M4 architectures. It's not really a prerequisite, but you need to know some basics about circuits. So if the computer scientists in this room, come see me, come to office hours, I can fill this in for you. You don't ever need to calculate voltages or know how instantaneous transient wave mumbo jumbo that you might see in 215. We need to have some intuition that if current goes through an LED, what happens? And if the voltage is high enough or low enough. So you need to have some intuition about circuits to be able to do well in this class. And if you don't, just come and I'll teach you how to do that. That's literally my job, is to teach you things.
My knowledge of circuits is only limited to redstone.
I don't know what redstone is.
It's like in Minecraft.
Got it. Perfect. As long as they have current and current goes through things, you're good. Okay? Current and switches, that's all you really need to know in this class. And I'll help you, the TAs will help you, Matt will help you, so I think you'll be fine. You just might have to spend a little bit more time. If voltage and current sound totally foreign to you, you just need somebody to help you get a little bit more intuition on those. So most of this class is going to be focused on Cortex M4 processors. We'll be talking about the instruction set. Okay, we're going to be talking about memory mapped I/O. This is the idea that how the core processor that you learned about in 370 interacts with the rest of the microcontroller is this idea of memory mapped I/O, and how the microcontroller or the core thinks everything is just a memory address. And we'll talk a lot about that throughout the semester. We'll talk about interrupts and timers, basically how do you do event-driven things on microcontrollers. Serial buses and communication, so how can you talk from one chip to another chip. And then we'll work with analog and digital signals, so how can you measure parameters of the world, how do you create sound or drive motors and those sorts of things. So a little bit of logistics. There are no required textbooks for this course. It's kind of one of the downsides of embedded system. It changes enough and is specific enough usually to a class of processors that it's not easy to have a textbook. However, if you like textbooks, both of these are pretty good. This one is written maybe for a sophomore level rather than a junior level, but it's very nuts and bolts. It'll tell you exactly how to do certain tasks, like set up timers and that sort of stuff. So I would recommend getting this. There you can find versions online. This is more what somebody out of college would use as a reference manual for the Cortex M4, M3 family. This has nothing to do, this doesn't really tell you about how the peripherals work, it will tell you how the core of the microcontroller works. So both of those are good reference manuals. If you can find a PDF online, that's a great place to start. Also, if you just want a cheat code of how to get a good grade in the class, I suggest getting one of those books. Grades are pretty. These are the breakdowns. What should I tell you about? So labs, midterms, we don't have, we have non-traditional midterms. We shouldn't even call them midterms, we just call them exams. So we have, it's like 5 weeks in the course, you have exam 1, about 10 weeks in the course, you have exam 2, and there's no final. You just work on the projects. So you just, after exam 2, you just brain dump, forget all that stuff, and then just work on your final project. Class participation, you will have, I will have worksheets to keep you engaged and have you practice problems. That is what you would do for class participation. You just hand them in, they're graded yes or no, or pass or no pass, and then they're randomly distributed throughout the year, maybe once a week or so. And then there's student presentations. About after the exam, the core content of the class winds down because we've kind of given it to you really fast, but then there's all these other aspects of embedded systems that you need to know about, like how do you drive a DC motor? How do you drive a brushless DC motor? How do you work with time of flight sensors? So as part of you preparing for your class projects, each group will give a presentation about some aspect of their embedded system that they're building, and there'll be more details on that later. Any questions? Okay. Yeah, we're going to give you an overview. Okay. In class, we'll give you an overview, perspective on the fields. We already talked about class participation. Oh, we do give out class participation. If you answer questions on Piazza, great. I'll make sure to denote that and give you those class participation points. I don't know how the math works compared to worksheets, but usually it works out by the end of the semester. Class schedule is online. At this point is pretty nailed down. If there's any discrepancy between this and Gradescope, please let us know. Whatever Gradescope says is the ground truth. We'll honor that. We might have to change the dates if you bring something up to us, but don't worry about 10 minutes before the deadline if this is different than Gradescope. You get about 7 homeworks. You'll get practice exams to review before the exams. Those are the exam dates and exam times. They're the same on the schedule. Labs are your opportunity to deep dive, right? I'm going to give you high-level understanding, hopefully, of like what the heck is an interrupt and why would you use it. Lab is your opportunity to really harden those skills in one specific microcontroller, right? And then many of you know there's a large, student presentations we already talked about. There's a large open-ended final project. You can work in teams of 3 to 5. You get to build more or less any crazy embedded system you want. So 473, they're like, you will build something that actually makes sense. My class is Rube Goldberg machines of embedded systems. Fantastic. There are some guidelines that we have. It has to make some amount of sense. It can't just be random bits flying around. But generally, we'll work with you to make sure there's something, a final project that you can actually achieve. That's usually what our goals are. There is a team formation event that we're going to make required this year. This really helps get people to actually find teammates and come up with a project. We usually have all the IAs and the instructors there, usually have pizza or something, and we just brainstorm. A lot of brainstorming. You guys will pitch ideas, and we try by the time you leave, everybody knows what group they're in and more or less what project they're going to be doing. All right, lastly, fair warning. Class has a large time commitment. I'm sure you guys can look at I don't know, what is it, atlas that tells you the time commitment that people think. It is a lot. We're trying to teach you real embedded systems, like you can leave here and actually be useful in the real world, not like playground embedded systems or like a fake instruction set. You know, these are real things that you can build your career on if you're interested. All right, so what do you get out of this course? So I think about this course and say that before 373, students have been studying engineering in the abstract, right? It's like, I have this weird class and they're teaching me about, I don't know, what compilers, or I'm teaching about, you know, some programming language over here, or maybe electrical engineering. In 373, you get to like take that, synthesize that knowledge, and to solve real world problems. You will actually have devices at the end of this class that do something. And you know, I think of this as a transformative class where you go from being an engineer in the abstract to actually being an engineer, in the best case. And you will look at the world differently. You will look at every device and be like, okay, I can build that now. Just about any device. You can be like, yeah, it's more complicated than what I built, but I know exactly how to make that wall clock up there, or that wireless, or that camera over there. You will know exactly how to build it and what goes into those things. And yes, it might take you a long time or a while to figure out all the little details, but it will be, you will know the basics. All right, so any course logistics questions? Okay.
Probably a bit early to ask, but like who decides the groups?
You do. And me and Matt and James will help you guys figure that out. You can, for labs, you'll have a lab partner that's in that lab section, but for your final projects, you can have people, work with people that are not in your lab section. Lab sections stop mattering at that point. I think the only requirement we say is like, we rather have 3 or 4, 5 or more starts getting unwieldy, and you don't come up with great projects. All right. All right, so now we're going to talk about the STM32 architecture. My goal here, I'm going to go real fast. It's going to be scary. You're all going to freak out, okay? Don't worry. My goal is to give you a high-level understanding so you kind of feel what it looks like. So when you walk in the lab, it won't be so scary. Then the rest of the course, we're going to dive into the details, okay? So I want you to focus on what components do, right, and how they fit together, rather than how they work. We will spend the rest of the class figuring out how they work. But I'd rather give you the overview architecture so that you're ready for lab this week. Okay? So you have a dev kit. This is the microcontroller. Oh. This is the microcontroller. So dev kit, this comes from the manufacturer. They're trying to give this to the engineers so that they have something to work on easily without having to make their own PCB. This is the ARM Cortex M4 microcontroller on there. We'll talk more about what each one of these words mean, but is this a specific class? And then that goes on the Nucleo dev kit, which is a product line from STM. Okay, so inside of that thing, this is the simplified architecture of that microcontroller. In 370, you guys learned about the green section, right? The core, basically, how you get instructions, fetch them, you know, do some basic processing, put them in register banks, add, subtract, whatever you're going to do. That's what you learned about, okay? Here, we're going to, generally this class is expanding beyond the core to all these other subsystems. So there's memory. Here we usually think about memory as unified flash and SRAM. We'll talk about the differences later. There's extra modules. These we'll talk about later in class, and the memory protection one we may never talk about, but these are extra functionalities to help control data flow through your device. These are all connected by buses. So buses are methods for sending large amounts of data throughout the system, and it's kind of a general purpose method for sending, you know, you can send stuff through a system bus and it could go to any one of these peripherals or to memory, right? So it's a unified architecture of how to transport data around the chip. So the simplified version of what a bus is, you probably remember from 370, you have a line of D flip-flops. You go and put some data out there in parallel, and then you can clock them into the receiver, the other side on a clock cycle. So this could be considered a very primitive bus. Every clock data is transferred from this register bank to this register bank. The only difference is with a bus is that you have lots of receivers, and there's usually flow control, like, hey, there's an address, I want to send it to this device or that device. But underneath, all it is just a bunch of parallel wires and a clock, clicking data back and forth between modules. There are some differences here. We have a high performance bus and a peripheral bus, which is bus architectures that ARM has developed that used to mean peripherals, as in all your peripherals would be over there, and this would only be for like memory and some other tasks. But now they've mixed them all together, so it's not, peripherals could also mean like GPIO and DACs and cameras and USB. So some peripherals are on the high performance bus. So the fact that it says advanced peripheral bus, don't worry about the word peripheral. It just means that this bus is for high speed things and that bus for low speed things, but this is also much more latency tolerant. That bus doesn't break if there's a blocking function as easily as the high performance bus. And this, again, is just to show you, hey, you have the core here and you're going to push data around, you're going to travel along these buses. And if you need to get some data from the core out to a GPIO pin, which is eventually lab 1, just conceptually you're going to have to push it through a bus. Now you guys, a lot of that will be absconded from you because you're just going to be doing loads and stores or writing data to a particular memory location. But under the hood, all this work is happening. And yes, there's a bridge between those two. We'll talk about that more in depth probably week 4 or so. Okay. Any questions so far? I know I'm going super fast. Don't freak out. Okay. We talked a little bit about peripherals. Peripherals are still in the IC. They're still part of the IC, part of the chip, with the peripheral to the core, being the ALU and the memory interfaces and all that sort of stuff. So peripherals are things like GPIO pins, timers. Timers don't even actually send anything out of the device. They're just there to keep track of time, and they'll throw interrupts, say, that the processor will keep track of. But you can also use some of the SPI or I2C or UART ports to talk to other devices. So peripheral just means peripheral or outside of the core, still on the chip. And lastly, there's a whole bunch of work. There's interrupts, and what you'll find about week 6 or 7 in the course is interrupts are the way in which we can stop normal processing of your instructions to do other tasks. So a user presses a button that can cause an interrupt that changes the code flow. You won't be doing that in this lab, but you'll be doing it in later labs. All right, so let's just work a basic example here. So say there's, again, don't worry about all the details. This is just about feeling. We're just feeling our way through how the processor works. So say you have in memory instruction space, you have this command, I want to load R0, R1. So this is the contents of R1 into register R0. And so you would take that data, it gets fetched, you decode it, and then you're going to perform the instruction. So here, let's say that was pointing at some memory in SRAM, so another memory address, and you're going to pull that into the core. And then say you want to store it somewhere. Well, the key idea of this microcontroller architecture is that memory, there's unified memory between your flash memory, SRAM, but also all these locations are just considered a memory location. That's it. So you want to go and put a 1 or a high on a GPIO pin, you're just going to write some value, your 1, into some register somewhere. So here, I think this is, we're going to store something. So here we're going to take that instruction, we're going to decode it, we're going to fetch it, decode, and then the instruction was send that piece of data somewhere, and in this example, send it over to the timer. I can reset the timer to something. So the overarching idea is I'm just going to use loads and stores to change register values inside your architecture. How many people are like confused and scared at this point? Fine, totally normal. I'm going to show you, we're going to look at back at these slides in like 3 weeks, you're going to be like, no, I got this, I promise. The goal is just to give you the high level of how it works. This is what the real block diagram and the data sheet for your dev kit looks like. Have all the same blocks. It's just, they just use small print. So you got your core. You got memory here. You got your DMA, your high performance bus, your low performance bus, or your peripheral bus. You've got some power management stuff, and then lots of different peripherals here. Oh, that's the bridge. And then here are your timers, all those sorts of things. Okay? So the same stuff that was in that simplified diagram is still in your actual data sheet. Okay. So we'll give you the primer on GPIO. And so this is an example of the chip that you have. This is actually a slightly different series, but it doesn't matter. I couldn't get a die image of your exact chip. And most of this chip is filled with SRAM and flash memory, and then the core is over here, along with some peripherals. Okay, so what they do is they go and take this chip and they put wire bonds on them and epoxy into this package. And those gold wires are actually connected to these pins out here. So these are example of pins that get soldered down to your board. And you can see that these will just go through the epoxy. And then that's what's soldered onto your dev kit. And then literally there's a trace that will say, you'll be looking at your data sheet and it'll say, connect a pin, this pin number over here is different than this pin number over here. So this is like your header pin, that's a pin on your chip. You're gonna have to figure out the mapping of, when I raise a pin over here, what happens on my dev kit, right? So you're gonna have to hook up your LED or your oscilloscope up to one of those pins, and you have to figure out, okay, if I put a register here, and how does that electrical signal map all the way through those pins onto that board and over there? And the lab will walk you through all that, but it's important to realize what's happening. Okay. So here we have GPIO peripheral. And basically you're going to be storing ones or zeros into that peripheral to make an LED turn on or off. And so there's a nomenclature here that we should clarify. You have register banks in your core, right? But we also call these, in here we also have registers as well that hold the state information of your peripheral. And so a register is just a collection of D flip-flops. It's a clock. In this world, it's a whole 32-bit architecture. So 32-bit parallel bits are going into these registers, and you can send data in, you can pull data out. So in the data sheet, you'll say, here's some memory address. Let's see. Oops. So in your data sheet, you'll say there's a memory address at this location, and it holds 32 bits. That's your register. That will be what your GPIO pin, that's how you can control your GPIO pins. So you can store into it, you can load data out of it. You'll need to know the address. All right, so the simplified diagram of a GPIO pin, the most basic sense, it is this a D flip-flop, right? So it's this is the output, this is the input, and then this is the deviation between the chip world and the outside world, and this is your I/O pin. You'll get some data from the high-performance bus. Likewise, I've flipped the pins. If you want to make this an input pin, data will come in, and there'll be a different D flip-flop. And I just changed those two D and Qs there. And that'll go off to the high-performance bus. So if we put it all together, this is what your GPIO pin more or less looks like. Okay, this is the thing you'll be controlling in lab. You have a pin that goes to the external world. There is a data path that goes into some register. Right? This is going to hold at some memory location. It'll hold whatever state was clocked in from the GPIO pin. You can control this to be an output. So the pin can be, this is why it's called general purpose input output. So you can control the pin with a control register to be an output, and you can drive 1 or a 0 out on that pin. Now you could read that pin too, you just know what it's going to be. If you drive it to be high and you read it, it's going to be high, but that is possible. Okay. This is called a push-pull pair, and I often, let's see if I have it set up. I often use false stats. Anybody use false stat before? Do you love false stat, or? All right, so some people who use it like it. Personally, I love false stat. All right, so here, this is all the circuits, oh, that's pretty small. This is all the circuits I want you to learn. All right, we're going to try. All right, so we're not really electrical engineers. We're computer engineers and computer scientists. But a transistor is a switch. That's all you have to know. It's not a variable resistor. It's just a switch in this class. And so we can look at this example. This is called an open drain circuit. This is similar to the some of the buttons that you're going to be doing in lab. And let's see, if I highlight this, the blue on the bottom shows you which trace it's going to go to. So if I short this pin out, it's going to drive the signal here to ground. If I open this up, this resistor is going to pull it up to VDD, so 3.3 volts. And so here's an example of, if I move this switch, I can make a pin on the exterior of my device go high or low. And I just want you guys to know this is the same thing that you would have in your microcontroller. Is this use a transistor, and it does the same thing. We can see over here, this goes to this trace over here, and there you can turn this one high or low. Okay, so that's as much electrical engineering as you need to know. There'll be LEDs. That's as much as you need to know. You can also do the same thing with push-pull pair. So this is how a pin will drive. Let's see, we're going over here now. We'll either drive the thing all the way to ground. So if I switch this pin is going to be low. If I switch this one, it's going to be high. And that's similar to how a GPIO pin works as well. So here we just have a push-pull pair. They use these so that they can push a lot more current through your GPIO pins, usually 20 milliamps to 10 milliamps. Okay, so you guys can, if you really get excited, you can copy down the URL. The entire schematic for this thing is held in that URL, and you can play with these as well. This is a little bit closer to what you'll have in lab. You'll have one GPIO port that's closing something down, right, open shorts. And so as I close this pin, I'm connecting VDD to this pin. And so we get this pin to go up and down. Hey, go up and down. It's not going up and down. Oh, because I moved it. Oh no. There we go. All right. And then there's some input logic. And then you, essentially in your lab, are going to be writing the glue. Obviously, it won't be a single wire, but you will have a lab where you push a button and you'll make an LED turn on. And just from a hardware point of view, the switch will be making that pin go high or low, and then you'll be driving it externally. And then the last one to show is this is more or less what the entire GPIO port, one single pin inside is. Now here's some registers. Again, you're going to be writing ones and zeros to these registers. Okay. You can, let's see, I got to run this thing. So if I go and connect a switch to it. So here's a switch, and I need, this port's disabled. If I connect this, you can see this pin, this register will register a 1 or a 0. And then if I wanted to, these are some LEDs basically. I can change the direction. I can use this control register to control whether this is an input or output, this MOSFET stage, and now I can control the output pin. Is that correct? So here, by writing a 1 into this register, I can control whether this thing is putting logic in here, is pulling this pin high, or whether it's pulling this pin low. I know, a lot of analog, you're all scared. This is as much analog as you're gonna get in this class. This is as much as you need to know. All right. What questions do you have about GPIO pins?
GPIO port on like the integrated circuit, or is that part of it?
It is part of the integrated circuit. So if we go, great question. All that logic that I was showing you is in this piece of silicon, okay? And then that's the way in which you will control whether a pin here goes high or low. So one of these bond wires will have high voltage or low voltage, will go out to this pin, and that pin is soldered, the whole thing is soldered onto this dev kit. And then there's some wire, I don't know where it is, that's just my guess because I didn't look at the data sheet, will go out to some header pin on the output. So that's what these things here are called, header pins, and you can connect your oscilloscope probe or your GPIO or your LEDs to. And so you just have to think about the whole path. You put a 1 into some register and electricity goes all the way through out to the external world. That can't be the only question. It's a great question. It can't be the only question, though, because I'm not that good a teacher, and I went way too fast.
Wait, so like, how do you control whether it's input or output? Like, do you flip a switch or does the processor manage it?
You, as the programmer, will have the processor control a register, and in this case, my simplified diagram is that there's a register called reg control, and in your data sheet, you will literally write, there'll be probably a 32-bit register that will control many GPIO pins, but one of those D flip-flops, or one of those register, will hold a bit that will control whether this is going to be input or an output or high Z. So you, as a programmer, will say, I want you to be an output now. And then you would, after that, then you could say, okay, now I want you to put in 1 or a 0 on that pin. What do you think? Okay.
So peripherals, are those things that exist in the IC? Like
Correct.
There was like a couple op amps, so those exist inside the IC.
Yes, so STM has chosen in some chips to put op amps inside because they know in the market, if say some PCB or some device manufacturer, they don't want to have external op amps because they'll cost extra money. So STM said, I'll put the op amps inside and allow you to wire them up just so to save you costs. But yeah, that's a kind of a weird analog thing you have on a digital chip in this particular line of microcontrollers. Okay.
What's an
That is the advanced high performance, bus, even though P is not a B. Advanced high performance bus. But basically there's the high level is that you're in the core, you're gonna write code for the core, and then you're gonna have to send, unbeknownst to you at this stage, when you write stuff into a memory location, it's gonna push data through that bus structure and get it into a memory location when you're doing stores.
The control register, when it takes
and basically the HP.
Yep.
The out register also takes it in, but the in register takes it out because it's
I think so.
the bottom is.
Do they take the same signal?
Yes. They take the same signal, but they would be at different addresses. I didn't show you all the details, okay? And we'll go through it in more detail, but this would have a different address than that would. And you basically say, go to this house on this street, and then do a task, and then this other place is another house on the street. What other questions? Yeah. Great question. Now, what you find here is that this real estate is expensive. In fact, one of the most fundamental challenges of integrated circuit design is having enough bandwidth in terms of pins to get data on and off your chip. So we don't want to waste pins by having them just be input or output. So we want to combine that functionality. And you can just see that there's only so many pins here, right? There's only so many I can get. So adding more will increase your cost. So that's the primary focus. You'll actually see that your GPIO pins can probably do 5 or 6 different things. They can be inputs, they can be outputs. You can connect them to an analog input. You can connect them to a DAC. This is where that configuration register comes in. You don't have to worry about that now. We'll talk about that later.
So you also such few pins and do like thousands of megabytes per second of data transfer.
Yes, I do know that. Generally, these things go at pretty fast clock rates. So in the digital world, you can do things fast. You can't do analog well at all. We'll learn more about that in this class. But as long as your clock is going fast enough with those D flip-flops to look at those edges, you'll be fine, right? So you put data in, you lock it in, push it off to the next place. So that's really the job of the D flip-flop, is to capture that information. The rest of trying to get to like a 100 megabit bus is a lot of dealing with all the analog. You want to make sure your traces don't have a lot of capacitance or resistance or inductance. So under a megabyte, you don't really have to worry that much about trying to get data in and out. Does that answer your question?
So why under a megabyte you don't have to worry about it?
Because the microcontrollers are fast and the parasitics are small at those, the effect of them are small at these frequencies, so just general board manufacturing, you don't have to worry about it. We can talk more about that later. Getting close to the end of class here. And I don't have any more slides. So the recap here is, we talked a little bit about this. You should understand market forces of why we're at